You're good.
All right, so here's the free body diagram. I hope you did this. There's friction. Well, mg is straight down. That's which way the planet is, so don't draw mg anywhere but there. Friction is always parallel to the surface, so make sure you draw it parallel to the surface. And the normal, by definition, is normal or perpendicular to the surface. Parallel to the surface, perpendicular to the surface. Did you draw the free body diagram like that? I hope so. Okay? Now, pick a positive direction. Which way is going to win? This way or into the board? Neither. So we can make normal force positive because nobody's going to sink that down in there. Which one is winning now? How about down the ramp or up the ramp? Well, I don't know, but let's take a guess and say down the ramp is positive and friction's not quite big enough to stop it from accelerating. I don't know. If I get a wrong answer, Christian, look what happens. If I say down is positive and I figure out my acceleration and my acceleration comes out to be a negative number, you know what that means? I picked the wrong way. That means friction won. Isn't that great? Even if you pick the wrong way, your answer is still going to be right. It just tells you that your direction was the other way. A negative A, when I figure this all out, just tells me friction was bigger than down. But step 3 now matters. Break up vectors into x and y components as needed. All right, now you got to tilt your head and pretend this is the x, parallel to the ramp, and this is the y, perpendicular to the ramp. Which force should be broken up into components? And the answer is mg. There's a component of mg right here and a component of mg there. In other words, Dave, sum of gravity is parallel to the ramp. When I go snowboarding, I like that component of gravity. It's my own weight that's making me slide down the hill. But there's another component of gravity that's pushing me into the hill, which, by the way, causes friction. You got to get to that part of the chapter. So the more it pushes in, the more friction I got. The more friction I got, the less I'm going to have fun snowboarding. So down the ramp and perpendicular to the ramp. Now we're ready. If that angle is theta, this angle is theta. Similar triangles. Read the book, you'll understand it. Put the tail of one on the head of the other, and you'll see that the parallel component is opposite of the angle, and the hypotenuse is mg. So how do you find the opposite side, which is the one that I need parallel to the ramp? Trig function, opposite over hypotenuse, sine of the angle equals mg, mg parallel to the ramp over mg. So the component of the weight that's parallel to the ramp is mg sine theta. If you ever go snowboarding with me, you'd yell out mg sine theta. That's the force parallel to the ramp of gravity. What about this piece right here? That's adjacent to the angle, so that piece right there is mg cosine of theta. So this piece is part of your own weight that's trying to get you to get pushed into the snow. And what's fighting it? The snow, normal force. This piece is the force of gravity that's parallel to the ramp. And what's fighting it? Friction. Now do you see that we had to break up mg into two components? Mg sine theta and mg cosine theta. Now we're ready to do step 4. Sum of all the forces in the y-axis cause the mass to accelerate in the y-axis. But nobody's winning. Normal force and mg cosine theta, nobody's winning. So there's no acceleration this time in this direction. So sum them all up. What do you get? Normal minus mg cosine theta equals 0. What does that teach you? That the normal force equals mg cosine theta. If it's on level surface, what's the cosine of 0? 1. So it's mg cos theta. mg times 1. mg. See, look, normal equals mg when you're on a horizontal bunny hill. Boring as heck when you go. Okay? So, mg cos theta equals the normal force. Get used to that. That happens a lot. Mg sine theta is the component of your own weight making you go down a hill. If you ever go skiing or snowboarding, that's the force trying to pull you down the hill. It's your own weight, but a little bit of it. What if you make the what if you make the steepness higher and higher and higher? Then sine theta gets bigger. Sine of 90 is 1. So what happens when you went down the wrong slope? Then you're going straight down, and mg sine theta is just mg. You're falling off of a cliff. Bunny hill, boring. Cliff, way too exciting. Somewhere in between there is comet, which is about 25 degrees. Okay? mg sine theta. So let's do it. Sum of all the forces in the x direction causes the mass to accelerate in the x direction. Okay? So that means, let's sum it up. Let's pick positive as down the hill, because I think it's going to win. mg sine theta equals ma. Hey guys, look at this. The m's go away if there's no other forces, and the acceleration is g sine theta. Doesn't matter what mass it is if there's no friction. Okay? So if there's no friction, this would be it. But I said there was friction. So look what happens when there's friction. Sum of all the forces. Let's sum them up with friction. mg sine theta minus friction equals ma. So now I got two forces duking it out, and whoever wins will cause the mass to accelerate. Okay? Now, when you read your book, you're going to find out friction is directly proportional to the normal force. Try that on your kitchen table. Rub your hand against the kitchen table, and there's a little friction. Make more normal force, and there's more friction. More normal, more friction. Less normal, less friction. That lab's coming up real soon, because I know you're doing it. Okay? So somebody came up with this little tidbit. Friction equals a coefficient of friction. You can look it up in your book. Every two materials have a different coefficient. Sand on rubber, rubber on cement, concrete on concrete, wood on wood. Every single one has a different number for the materials. Multiply that by the normal force, and it'll tell you, if it's moving, the coefficient of friction. If it's not moving, it's a little weirder. The frictional force is less than or equal to mu normal when it's not moving. Mu is static coefficient, kinetic coefficient. Okay? All right, so these are the equations from the book. Now I could plug that in for friction. mg sine theta minus friction, mu normal equals ma. But what's normal? We just found out what normal was. I circled it up here. So it's really mg sine theta minus mu. And what's normal? mg cosine theta equals ma. In other words, the force parallel minus friction equals ma. And look, the m's canceled, and it doesn't matter what the mass was that was going down the hill. And now a is g sine theta, which what it was when there was no friction, minus mu g cosine theta. That's what the acceleration down a ramp would be. Weird looking, scary looking, but they'll give you mu, and you can find a. Or they'll give you a, and you can find mu. G is 9.8, and they'll give you the angle of the ramp. All right, stop there. Thank you.